My name is Alina. I'm the project manager for Wizard's Chess, which was an idea based on the like end of the movie Harry Potter scene where they played basically like life-size chess using like their voice commands and stuff. And we kind of just wanted to replicate that and create a giant chessboard with large robots that responded to voice commands. So our finished product, like not right now, but like in the long term, would be a large field and chess pieces, and each of the chess pieces would be able to map where they're supposed to be, avoid collisions, have some awareness, and like be able to figure out where they're supposed to go based on voice input from the players. And so that voice input would be converted into a field position, and then using that and like our software control center, which is like the hub of all the processing and coding, the robots will be able to use that and move to the correct spot and then determine if it's like, I don't know, like a check, a take, a valid movement or not. So we kind of had a design iteration. We first started with a four-wheel robot. We kind of wanted an X drive because that's pretty cool, and we thought like it would be easy to move forward, backwards, side, diagonally, whatever we needed. But we looked at the budget for that, and it was really expensive. So we decided to go to a more triangular shaped robot made out of wood. So like wood and metal. So this triangle here would be made out of a wood frame, and then the bar across the middle would be metal. So this is like, so the one on the left is like our rough sketch and stuff, and then the one on the right is our first CAD model. And then our final design is something that looks like this. So we have the wood frames, the metal in the middle, we have the microcontrollers in the center, and then 2 wheels, 2 motors, and then ball bearings, which would just make it so that we have a third point of contact and just smooth movement all around. It doesn't really, there's no motor attached to it or anything. Our budget. So we first had, like, on the left, we have what we thought we would be spending for 2 robots, a control center, and like making the field. So that was about $370, which is what we got from Pepsi. Once we started actually finding the parts, we figured out that like each robot would probably be around 50 to 60, and the total pricing would be $354. But that total does not include tax, shipping, and like we had some interesting idea, like ways of how we figured out the price for each robot. So it was kind of just like take the title price and then divide it by how many parts we need. It was really scuffed. So once we actually started like buying everything, we figured out that our running total was about 420. So unfortunately, we did go a little bit above budget, but each robot is only about $40 now. And so that extra money went towards having a better control center, so better software processing in the future. Our timeline looked kind of like this. So February and March was spent a lot on designing and planning and figuring out what we wanted to do and how we wanted to approach this project, and then software creation. And then March, we like planned our materials list. We started ordering parts. We got those in April. It's really only been like the past 3 weeks where we've actually been able to meet up and start actually building these robots and trying to integrate the software. And the reason it like took so long is because it was really hard for me to get into Bechtel, especially since like I've never used the system. So that took a while. And then we've had some trouble with our Raspberry Pi not connecting to the internet. And so those were our 2 main obstacles and like why it took so much time. And then going forward, like in the fall, obviously we're going to look to complete all chess pieces. We're going to start with like full software implementation and testing. And then our sensors, like we're thinking about maybe adding more sensors to refine the movement of the robots, like color light sensors. We have gyro sensors or proximity sensors. And we were thinking like maybe in the future we could have a camera overhead that would be like analyzing what robot is what piece, and then that would be able to figure out like that would be taking in the voice inputs and sending like, oh, this piece needs to go there, so do that, and like it'll detect those objects. So then I had some pictures or videos. So we had of like what we've been doing. So this is our robot. This is at Bechtel. We were just like putting it together. So it started coming together. This is the robot on the field painted. It has most of the parts. It doesn't have the microcontroller yet. Here's another picture of that. So it's pretty big. It's about like 10 inches by 8 inches. So 10 inches on the bottom, 8 inches on the across the vertical. And then here is a video of what we were able to do. So we were able to get the wheels to move like back and forth. This whole thing there, that's like, I think it was like a voltage converter because we needed, or like a voltage booster because we needed more power. And then the code that's running through this is from the Raspberry Pi 4. So yeah, and then I just wanted to turn it over to our software team and let them talk about the software.
So I can start since it's about the command center. So initially, let me just share my screen. Initially, we were trying to also simulate everything, but since we got so far with the robot, we decided to just create this like the whole environment so that we can actually test it with the robots. And so now what we have is we have an ROS that basically can wait for the input from the user. It varies like output 0 and 9. Those are just some values. And it waits for the input from the user. It reads it, it sends it to another node. And this node, if we connect it to Bluetooth or Wi-Fi or like whatever we want to communicate wirelessly with the robot, it will send those coordinates to the robot. And then we are still thinking whether we should do the path planning here or in the robot. That's gonna be what we're gonna decide during the testing phase. And yeah, that's about it for the command center for now. We also plan to implement the chess algorithm after we get one robot to move, so that we can, for example, write PA5, which is pawn, and A5, and it will automatically detect what piece should move and where.
Hi, I was looking into...
Yeah, so I can pick up kind of what Adam left off with. And so what he was showing is kind of the robot controller side of things in ROS, which will kind of do the planning. We also have a Python script, an entire algorithm that computes the chess moves and will keep track of the chess game. And so that'll be making sure that all the moves are legal and also kind of determining which piece to move, where it needs to move, you know, whether it's a check, whether it's a capture, whether other pieces need to interact with it and that kind of stuff. And so from a software side of things, the kind of whole flow chart is that we're going to have a command center, which is connected to the Raspberry Pi 4, and that's going to do all the voice processing. So Aaron, he wasn't able to make it to the meeting tonight. He had to work, unfortunately, but he's been working on that and getting and training the speech recognition software, which the player will use to kind of, they'll say pawn E4, the software will recognize it and give a string code to the chess algorithm, which will then input it as a chess move, make sure that it's a legal move, that it can be commuted based on the game, and then give the robot controller, as Adam was showing, a set of starting coordinates and a set of ending coordinates. And then from there, it'll plan the path And eventually when we start implementing more sensors and camera, it'll be a lot smoother of a process with the robot moving and maybe interacting with other robots if robots need to move out of the way or if a capture needs to take place. And so that's once we finally get kind of the robot built, and then like Alana was saying, we had some issues with the Raspberry Pi, so we weren't able to fully test all of the software functions, but that'll be our first round of testing, is getting robot movements and making sure all those communication nodes are working, and then adding layers like sensors and more live planning and path planning to it as well. And so that's what we'll be working on moving forward.
Yeah, so that's about it for Wizards Trust.
Okay. I actually have one question first. I was looking like from the budget. Have you guys like actually been reimbursed for your expenses yet? Or are you still waiting on that?
Oh, at least I'm still waiting, but I only put mine in like a week ago.
Okay. Yeah, because I know the Google form like is there to put stuff in. But like no, as far as I know, none of the officers actually go and check to see if there's data there. Like someone has to poke us and tell us to.
Oh.
So I just wanted to check and see if anyone had handled that yet.
Yeah, I'm still waiting for reimbursement as well.
Okay, so we'll try to make sure you get those before the end of the semester, because it's going to be significantly harder to pick up checks at Kroc if you guys aren't at Purdue.
Yeah.
Mm-hmm.
And then more of a technical question. I know earlier in the year we had you had talked about like what level of and like even now you had discussed it, like does the path planning happen on the robot or on the control center? Like what are your current thoughts on that? Like what do you think of like the pros and cons of like each one, and how are you feeling about that?
So one of the pros of having it on the command center is that like we don't have to spend as much money on each robot putting like the sensors and everything needed, because we're gonna need like 32 of those, and that's a lot. So and then like one of the cons is it's not on the robot, so which would be pretty cool to have, but
yeah, because I mean that's sort of where I'm coming at too, is like I think it would be really cool for each robot to be like independent, but of course that puts a massive, you know, burden on you
like
guys.
that would definitely be the goal, to like have each robot be fully aware of everything that's going on. But since we have like the cost restraints and everything, it's just more beneficial to put it in the command center.
Yeah, and I guess that sort of leads me to a similar question, which is just out of curiosity about like your current discussion on the sensor feedback you're going to be using. So if you were to go with an approach where you're doing all the path planning from the, I guess, I'm blanking on the word that you've been calling it, but like the command center, I guess that would sort of require that you're primarily using some sort of camera to do a lot of that sensor detection and get an understanding of where the objects are within the field and how to coordinate and move to the desired position. Is that what where you're most leaning towards in the future as far as like sensor feedback?
Yeah, for if we're planning to implement this like one command center that commands it all, we're mostly leaning to the camera that oversees everything. But I mean, it all depends on testing. We're also looking at some other approaches, like with gyros or like path planning in every robot using some graph searching algorithms. So yeah, I would say we have to test those approaches to determine which one is the best.
And then following up from that, so it looked like from the pictures that you guys had the RFID tags already implemented within the tiles of the field. I guess I was sort of curious about like if you took an approach where you had the main sensor feedback and path planning coming from the like headquarters, where would those sort of play a role in the overall scope of control, and how would that data sort of be fused in is where I'm sort of lost.
Yeah, so I can comment on that. The RFID tags is mainly to make sure that, like at the beginning, ending of the turn, the robots are kind of centered on the squares. Based on at least the research I've done on the RFID tags that we got, the like reading distance is not very big. It's enough to be read by a tag, a piece of software on the robot. But if you were, like all the way off to the side of the square, you might not get that reading. And so the idea with having the RFID tags centered on each square is that either the command center or the robot would know, hey, either I'm centered where I need to be, or I'm not centered where I need to be. It also can confirm that like the pieces are on the right squares, because if we either write or just read the tags beforehand, we know which tag ID corresponds to which square. And so if we tell, a robot to move to E4, and then it finishes moving, sends the data back, and it sends the wrong tag ID, then okay, we know something's wrong, and either we need to write a kind of control system to figure out what went wrong, or maybe at the beginning just have some kind of manual inputs. And so, and then another thing we were talking about, if we were to do kind of like a robot lead on the movement, is also doing it like square by square. Like, so instead of planning the entire path, it's like, okay, I just need to go to this square, read the RFID tag, and just kind of make sure that you've reached that square correctly, and then you can kind of go to the next square. So that was kind of the point. When we initially had kind of thought of this idea, we didn't really think much about like sensors or camera detection. RFID tags were kind of like a cheap way, at least a starting point, a building block, as just kind of like a second, make sure that it's all centered. And that way it can be standardized. All the pieces, when they're not moving, are facing the same direction, are in the center of the squares. And from just like an appeal standpoint to the players, looks more formal, and they can kind of gauge instead of like having pieces, on the edge of the square. Plus also helps planning, just knowing where the robots are without actually like knowing the exact locations.
Yeah, I could definitely see an advantage for helping with the initialization of the game. Awesome. Thank you, guys.
Any other questions? Okay. Well, awesome work this semester. I think you guys did a really good job of like starting the project from nothing, and like making, really good, like methodical approaches to solving it. So, okay. Well, I think Rocket League is next. So I'm gonna share my PowerPoint. Okay. Can everybody see that? Okay. So just quick reintroduction to what the project is. So we're trying to recreate the video game with the same name in real life using RC cars. So it's like an online multiplayer game, and the part of it that I found most interesting is like how you have 3 people versus another 3 people, and like you have to work together to play soccer and get the ball into the goal. And so I think if we get each car independently controlled by some autonomous entity, I think it would give us a really cool research opportunity to play around with collaboration versus competition, and how do we get like neural networks or whatever we end up using to work together and also like compete against others, and just lots of really cool behavior. And it also exposes a lot of different levels of robotics, because we are working with physical hardware with the cars, and like that's hands-on electronics, but then we go all the way up to like the HighLevel Planner, which is just pure software. So I thought it gave like a little bit of like everybody has a little piece of it that they would find interesting. So in terms of so this is the second semester that the project has been active, and this is what we accomplished in the first semester. Essentially, you are looking at a really low budget prototype of the system. So we had just a very simple RC car that I had already owned. We had a really hacky way of controlling it from ROS. It involved an Arduino and doing things with analog control that we probably shouldn't have done because they weren't very robust. Instead of tracking the location of the ball, we just stuck an April tag right next to it, We had no field. Instead, we have a cardboard box there for the goal. But it was sort of a really good proof of concept to show that like a lot of the different systems that need to be in place for us to be able to control an RC car to push a ball into the goal, like we were able to build a lot of that to have it working at some level, even if it wasn't very robust, very accurate. But it was sort of like a good first step. And then last thing I'll comment on is that there's only one camera, which, you know, spoiler alert for later in this presentation, upgrading to 4 cameras was a non-trivial task that hasn't been fully done yet. So our planned deliverables for the semester, we wanted to have a face-off between 2 opposing cars. And so this is sort of a simpler way of getting at that same level where you have 3v3, like 1v1 is sort of smaller, cheaper, easier to get to, we'd figure. And then we'd be having a lot of time, in theory, to do a lot of that testing between human and autonomous agents. So in terms of what we actually accomplished, we made it a decent way towards getting 1 car with fully autonomous capability. We sort of split the project into a lot of different chunks, and each chunk is actually fairly robust in itself. But then whenever we try to integrate it all together, we run into issues. And so a lot of next semester is going to be debugging those issues so that we can finally get like the last 10%, so that we can have 2 fully autonomous cars. Our budget for this semester was fairly large. We were bringing in $1,500 from SOGA, and then we were planning on spending all of it plus another $325. And then that $325 basically comes from the fact that we're purchasing cameras, which are fairly expensive, and they will live within the club long past the project. Whereas a lot of the other stuff like the RC cars, building materials for the field, like they're more, you know, project specific. So we got a little bit of an allowance to go over from that. And then in terms of how we kept to this, we were only $50 over budget, meaning that we spent about $375 past what we brought in from SOGA. That take that as you will, if that was good or bad. So then here's the system outline. So each like colored element is sort of one of those chunks that I talked about earlier that we've been working to debug. And that's how we'll organize how we talk about our progress in the next couple of slides. So we're going to start all the way at the lowest level with like constructing the physical field elements, and then the RC car that needs to operate with those. And then we talk about the ROS interface, which is controlling the car from the computer. And then the localization and sensor system, which is responsible for using computer vision to identify all of the objects on the field from those cameras, and then give like an accurate location to the software so that it can do stuff with that. We're going to skip over the low-level controller since that was not much progress happened on it since last semester because it like worked fairly well. And then we'll talk about mid-level software, which is that orange inside the dotted lines there. And that's responsible for receiving a trajectory that the car is supposed to execute and then actually making it happen. And then we'll finish with the HighLevel Planner, which is this deep reinforcement learning system responsible for a lot of the overall strategy of the game. So I'm going to hand it off to Nick and Adit now to talk about the field construction.
So we weren't responsible for the actual physical hardware of the project. The image on the left is like our full field setup at the end of this semester. As James mentioned earlier, they had what an RC car, a cardboard goal, and 2 chairs with aluminum. We've got a full wooden field, 10 feet by 15 feet with 4 tripods, PVC going across with the cameras. The middle image shows how we actually connect the wood. We use 2 dowels to pin them together so there's more stability when the ball actually hits the walls. And the third shows our camera mount for the FLIR and Basler cameras that we plan on using when the aluminum is set up for the tripods. For next semester, our 2 main priorities are to get full aluminum mounting and to get a full 4 camera setup once it's done, once it's also possible by the software side.
Yeah, and then the aluminum is replacing the PVC in case that wasn't clear. next slide, right?
Yep.
Yeah, next slide. So this is the new car on the, so on the left is like the original stock hardware, and then on the right it's the ones we replaced. So some things we added or changed was we added a new servo motor for the controls for making the car turn left and right. We added a new motor controller and a receiver that uses the FreeSky transmitter. And next slide. And it's just a quick video comparing the three cars. One was the last year's car, and then the middle one is the original car, and then the left one is the one that's modified. So yeah, I mean, like the new cars they bought is already a step up from the car from the last semester. So, and then next slide. And then this is just like how we control it. So this is like the FreeSky transmitter, and then we hook it up to a Teensy 3.1. And then we use ROS serial, and basically there's like a ROS node that sends serial inputs to Teensy 3.1. And then Teensy 3.1 sends uses PPM signals. So I think last semester it was all analog signals, and they hooked up like an Arduino directly to the controller, but now it's all digital now, so slightly better.
For the perception system, last semester, as James said, we had 1 camera, and the plan was for this semester to scale up to 4 cameras. That ended up causing some problems, so we scaled that back down to just 2 cameras. And so the problem we were facing was we had to get the data from the 2 cameras and somehow localize it so we get one coherent view or like idea of what's going on in the system. To do this, we had an able tag that was visible in both camera frames, and we used that to get the position from the cameras to the able tag. From that, we can determine the position of other things on the field. And if you press play on that video, you can see that on the right is the TF tree, kind of showing the current state of the system. And see if the car stops for a little bit, it updates the position. Yeah, there's a number of problems with this as it stands. When the car is moving, there's way too much motion blur for us to tell like what's happening. So we need to develop a more robust system to deal with that. Also, not immediately apparent in the video is that there is an extremely high latency on the Jetson between something moving in real life and it showing up on the camera to it being reflected inside of ROS. And that's mostly due in part to the package we're using, TF. It introduces a lot of latency, so ideally we'd move away from that. And as I said before, we're having problems with adding more than like 3 or 4 cameras. So we need to either offload image processing to separate computers that aren't the Jetson, or modify the driver that we're using to be able to handle more data. Yeah, pretty much wraps it up.
Okay, so for the ball tracking, we're using OpenCV thresholding. So essentially, it does a color filter and it filters out colors that aren't, in this case, blue. And then we basically, to get the camera position to the ball position, we just project a 3D array and do a bunch of trig. It's pretty boring. And then we're using a predefined 0 point to combine the 2 cameras, which is like my sort of alternative to not using the TF tree. So I mean, it says it's much simpler than TF tree, and it works pretty well. If you click on the video, now this is a little bit choppy. That's just because of my laptop and the fact that I'm rendering these frames. Generally, if I'm just outputting like the coordinates to the screen, it runs like at like a good frame rate. You can see it's following, puts the red dot on the ball and it follows it all the way through its entire path.
All right, so now we're on mid-level software where we are trying to take the localization, the information that's being brought in, and then so we know where the ball, where the car is, and then we are given a goal position to take the car to get to, and a goal for like when to get there and what direction to be heading at what speed. And then the mid-level software tries to make that happen by one part is the trajectory planner, which creates a path to get from where the car is to where we want it to be. And so last semester we had that working to some extent, but we made a bunch of upgrades to it this semester. So first of all, we added the ability to make backwards paths, which is really important for the car not to get stuck. And then we also added some extra information to our path. So before it only determined what position to be at, now it also publishes the time and the velocity that the car should be moving at when it gets to a certain waypoint. And then finally, we added in some checks. So we have, and now we give a score on how feasible the path is and whether we can meet our goal. And then we also check in case we have problems with curvature in our path. The remaining things that we want to do is mostly just adjust our parameters to match the simulator and the real world and make sure that the car can follow it. So especially looking at curvature and making sure that our paths that we generate are ones that the car can actually follow.
So looking a little more at the waypoint controller, we're still within that mid-level software stack. This is just another one of those middlemen and the mini cascading feedback loops we have going on. This portion of the system is primarily responsible for taking that path we're given from the trajectory planner and determining the proper commands to be able to hit the waypoints along that path. And so you can sort of see a demonstration on the right where we're sort of given a look ahead circle and then seeing where along that path we're going to be aiming for and what commands will properly align the wheels and our sort of linear velocity to reach that and follow the path appropriately. And as a common theme for the mid-level software stack, a lot of the work we did this semester was just sort of fixing bugs from the previous semester and refining the process a little more, while some other areas of the general system sort of made progress. Specifically with regards to the waypoint controller, like I said, resolving some bugs, especially within the math that we're going on, but then also adding additional capabilities. So being able to handle backwards paths and just adding additional information in preparation for when we have the high-level planner fully working in this system, just necessary information about the error we're sort of experiencing while following a path, how far off we are from our expected destination time, and how do we sort of manage those sort of errors. Also similar to the trajectory planner, we're primarily going to be looking at just tuning the system a little more, as setting the parameters. One of these parameters includes this look ahead circle, which will be just something that requires running this on the real world system and iteratively tuning to find a value that works for the setup we have.
We have also improved a bit upon the simulator that we had from last semester. So we've removed the maximum speed. We updated the dimensions to fit what the actual field and car will be. We made a more intelligent acceleration. So instead of going from maximum acceleration to minimum acceleration, or maximum braking, we determined what is needed to reach the optimal speed. We moved some parameters to a YAML file, which is just refactoring. And overall, we think the simulator is doing pretty well. We think that it provides good testing for the waypoint controller and trajectory planner, and it will allow us to make high-level training. So if you could play the video. So this shows that the ball is approaching the ball, which is purple, and it should score. There we go. That's a go. Yep.
Goal.
Yeah, that's it for me. Thanks.
Okay, now moving past the mid-level software up to the high-level planner. So we realized that Rocket League is a complex challenge to solve using deep reinforcement learning techniques. We realized that pretty early on as we were looking at papers. So we decided it would be an easier task to solve the snake tutorial, like the game of Snake and Ross that everybody knows and loves first, because we figured it would be a lot easier. So I can show a quick video of its performance on that. And I think that this video, I can play it again because it's pretty quick. You can see it got 1 apple, 2 apples, and then ran into a wall. And this may actually overplay the performance of our agents on Snake. It was actually quite abysmal, pretty bad at it. And we learned there that, deep reinforcement learning, even for something that seems easy, like playing a game of Snake, is actually very complex. So we really sort of underestimated the challenge that the high-level planner would be for us. But a few of the really good things that I think we accomplished was that we made a fairly robust ROS interface. So rather than having a direct Python to Python interface in order to do the high-level stuff like using PyTorch and autonomous learning library to build these agents, we actually use the existing ROS network for training. And we have a way to mess with the way that time works inside ROS by putting it in a simulation mode where we can increase the real-time factor. And so we can train 5,000 episodes of Snake in about 1.5 minutes, where each episode, I don't know, takes several seconds at least. And we're able to do that all through ROS, which is nice because in the future, whenever we're working with Rocket League, we are going to have to use the mid-level software in the system as we're training. And converting all of that, making it twice, once using ROS and once using just Python, would potentially introduce a lot of bugs and be a lot of extra work. So being able to reuse that ROS interface was nice. And we sort of tested that with Cartpole. Since we didn't get the performance that we were hoping out of Snake, we decided to take it a step further down and work on Cartpole. And this is the equivalent of trying to balance a broom upside down on your fingertip in 2 dimensions. And so this is considered like a toy example. And for any modern machine learning system, it should be very simple for it to learn how to do this. And so we built it twice, once using the ROS interface and once without. And we were able to show that for the same hyperparameters, we had fairly similar training dynamics, which was nice because that proved that the ROS interface worked. And instead, our challenges with Snake earlier were with Snake itself and not with the ROS interface. And then one final thing, if you look at the training log, everything is normalized between 0 and 1 in terms of, and basically that's how well it performed. So close to 1 is good and close to 0 is bad. And you can see that it achieves a perfect game after 1,000 episodes. But if you give it more time to train, it actually oscillates fairly wildly. And that's common in machine learning, we found out. And so even for a toy environment like this, something that should be pretty simple, this hyperparameter tuning is very difficult. So that's why a lot of our focus in the future is going to be working on building a more robust tool set to do hyperparameter searches for us automatically rather than manually. And then eventually we will be applying this ROS interface to Rocket League itself, now that we have a really fancy sim to do it in. So we talked about future work with each sort of item earlier, but just to summarize for the entire project, we need to continue to work on our physical field elements, specifically the camera mounting. And then once we have that, we need to resolve camera issues in terms of both hardware and software, because the Jetson itself, it seems, doesn't have the capability to handle all that data. And our software is also going to be really slowed down by that. Continue to work with the simulator, and then eventually wrap that into the deep reinforcement learning system. Before we finish here, I just want to thank people who are leaving the team this semester due to them graduating. So Adrian finished his undergraduate, and he's going to be moving on to get a master's in management. And then Ruben finished his graduate, and he's going to be moving into industry. So thanks for your work on the project. Lastly, any questions for the team? Okay. If nobody has any questions, then I guess we can move on to robot arm.
Sounds good. I'll share my screen. Right. So I just want to start off by kind of mentioning the purpose of the robot arm project. Initially, we were kind of excited about the idea of having our own custom robot arm, and that can kind of do what we want, kind of be on our table and be extremely helpful and do different things. And during this semester, we kind of like transitioned as well to kind of noticing how we can use vision and understanding how we can make robot arms smart and what makes them smart, and also just the dexterity of like a robot arm to be able to accomplish a variety of different tasks. And so we intended this semester to like push that all down into, or actually now moving on, actually this is what we did last semester for just to be able to simulate just a robot arm or as a hand that was able to pick up an object and place it to another location, just a simple pick and place, and truly just understand the kinematics going on when moving a robot arm. And this upcoming semester, or this semester, we plan to incorporate vision and improve the robot arm design. And that, so given that this was kind of our projected deliverables, we wanted to, as I said, focus our kind of our initiative towards building a game of chess, having the robot arm play a game of chess. And with this, it would include kind of all of the aspects of vision and also the kinematics that we developed last semester. And we also wanted to publish that as well with a tutorial. And with the kind of what we were able to complete this semester, we were able to develop a gripper that we'll be showing next of a robot arm gripper that was able to just pick up the chess pieces with different uncertainty as kind of more specific to the task. And then additionally, to address the vision that we wanted to build, we were able to develop a object detection using YOLO V5 that was able to detect all the chess pieces with 90% accuracy. So now I'll hand it over. I think the slides got a little messed up, but so I actually also just want to, before we get into actual robot arm, also just wanted to review the budget as well. So the predicted budget, we kind of aimed mainly going to be the cameras, as they were new additions to the systems, and 3D printer filament, and additional, since we're adding a new gripper parts. And that when the actual new additions that happened was did some miscalculations and realized there were also some servos that weren't working. So we had to add that on to the list, additionally with some accessories for those servos. So now we can finally move on. I'll hand it over to Sarah, who will now talk about the hardware aspect of the arm.
So this semester, at least, the hardware has been definitely an adventure, to say the least. We, beginning this project, were determined to, or at least I definitely was, to make a robot arm from scratch. And one of the main things we learned was not necessarily a good idea to have to build everything from scratch. So we designed a 6-screw freedom robot arm that performed reasonably well mechanically. However, we did run into a lot of blockages and issues with the controls using the Dynamixel servos. Having not had a whole lot, having zero experience with Dynamixel servos specifically, and not a whole lot of experience with the fancier servos, anything fancier than a PWM servo. It was very difficult to figure out how they worked.
So the majority of the time was spent debugging, which was pretty unfortunate. So now it's clear that next steps would be to look into probably some alternatives, something a little simpler, something a little bit better documented than Dynamixels, which we've had trouble finding good documentation on them. Yeah, that's pretty much a summary of this semester and the hardware, at least for the 6th degree of freedom arm for this semester.
Sounds good. And now moving over to the gripper, Pranav will speak a little further on that.
You guys hear me? Yeah, okay, cool.
Yep.
So basically for this semester, one of the key things we identified was that we need a different kind of gripper for the chess pieces, because the initial one was a flat, the fingers were flat, and so gripping chess pieces and things like that would be very difficult. And also since the error for placement is very small, and we don't want any pieces to fall or to land at the wrong angle, we decided that we need a different kind of finger design. And so for that we came up with what you see on your screen. It's essentially cylinder which is cut in half, and so each half of the cylinder acts as a finger, and in between the cylinder, around the lower bottom area, I don't know if you can see it properly, but there is a sort of a ridge, and on that ridge basically helps the pieces hook onto that the pieces basically hook onto that ridge, and so they are very stable. What we've done is that we've taken that ridge, and on top of that we've also added some foam. That way now you have a cushioned padding, and you have that ridge-like design based on which the pieces sit. And since almost all of the chess pieces have a certain lip that you can see over there at like different points, and so once the pieces sit onto that ridge, they are very stable. In fact, even a very small amount of force can hold the pieces upright, and it can move them around without the pieces falling out. And another benefit of this design is that there's very little actual chance of the piece toppling over, or even if the robot arm places it the wrong way. For example, if the arm comes in at an angle and tries dropping it, since it's a cylindrical design, it opens up in such a way that the piece lands upright, and it doesn't fall over. And this also allows us to grip and pick up pieces without actually disturbing anything on either side. Because it's such a small and simple design, it occupies very little space, and so the gripper doesn't actually hit any of the pieces nearby. And so that's how the team has worked towards solving the hardware challenge of the gripper. This is a small demo of the robot arm picking up pieces. As you can see, even if the arm doesn't open perfectly, or there is some problem in that area, the piece always more or less lands upright. And so that's one of the main benefits from the circular design. Yeah.
That's good. So I'll hand it over to Anoop. We'll talk more about the camera mount that was also designed for the robot.
Yeah, so I spoke with a few people, and they wanted to add a camera mount for, I believe it was the robot that was made this semester. And so originally we had a mount that had an angular degree of freedom, but then we determined that because of the servo that's right behind the camera mount, there was really no need for there to be any extra rotation in the camera mount itself. So what you see on the right-hand side here is the final version as of now, which has the mount itself fixed to the bracket with a slot in the middle for cable management. And actually, originally, this mount was on the wrong side of the bracket, and that was just a result of me not knowing what their orientation looked like. So I had gone to Bechdel and checked it out and fixed it so that it looks or works with the way that the pieces are supposed to be picked up. And yeah, so what you see in this middle picture right here is what it would look like if the mount was attached to the current robot. And in the future, it may be necessary to add that degree of freedom if we determine that that's needed, or it could be useful to change the location. But whatever we decide to do, it'll just be important to make sure that the camera mount orientation follows or is designed around how the pieces are picked up.
Good. So for visual servoing, and which is essentially getting the arm to move to like a design specified location using vision. And for visual servoing and the kind of other software kind of things you mentioned, like one word would describe it as a lot of pivots. There were a lot of kind of issues with libraries that we used, after spending a lot of time getting it to work within ROS, having like a low frame rate, for example. So a lot of kind of issues like intermingled with each other that kind of allowed us, and also given the fact that we didn't have a hardware system to test vision on, made it really difficult for us to make a lot of progress. So ultimately what the pivot ended up being is to start moving to a simulation-based approach for testing. So as you can see in this video, you'll be able to see, I guess, the kind of the operation of the entire like Move It system, and the which is the tool that allows us to move the robot arm to specify locations, all being able to move kind of in the simulation. So it allows us to test vision as well. So being able to import a camera into there to test the object recognition and also the visual servoing. So the actual visual servoing piece never fully materialized due to just not having enough time. So that's for a future semester, and something we can actually be able to test maybe a little bit in the next few days, where we're like really close. So just off by a little bit of time. But overall was able to get some decent progress in a system that we can use for future work. And additionally, we wanted to have a system that uses reinforcement learning as well, so the robot arm can learn how to pick up stuff instead of us kind of per se like using a lot of manual controllers that were hard coding to do a certain task. So Gazebo has that functionality and having that interface to be able to do that. So that will set us up for future project progress. So now I'll hand it over to Vinita, who will be talking about the data set that was developed and to do object detection.
So I created a custom data set to detect each individual chess piece and classify them. So the first set of 300 pictures that I took, I played a chess game against my friend and took pictures from different angles. So when I did a data set health check on RoboFlow, I realized that the pawns were overrepresented just because there's so many more pawns compared to other pieces. So I continued to take more pictures to make up for that, so that the other pieces would also be well represented by the data set. And because I did all of that, I doubled the number of pictures I took and tried taking more of pieces that I thought were very similar, like the queens and the bishops. So when I was annotating, I sometimes had trouble differentiating between the queens and the bishops. And I was also worried about the knights not being recognized because they look different from different angles. So I tried to take more pictures of those specific pieces too. So when we tested all of that together, it identified the chess pieces with over 90% accuracy.
And additionally, to add on to that, like given the fact that there weren't any data sets out there that were good enough for our application and we're able to have all the angles that we were looking for, and we're able to be trained by a model that would have a fast inference rate on something that which was my computer, which is 8 GB memory, no GPU, and still 15, 20 plus frames per second, which using the YOLO v5 plus the data set that was trained, ended up working quite nicely, and would fit right into the visual servoing system once that ends up working. So overall lessons learned, kind of just some things I just put together of kind of one thing was that there was a lot of project knowledge that was kind of centralized, and we want to put that into like tutorials and videos and documentation and graphs, and want to make sure that new members are able to learn kind of what we've built so far, and be able to and make sure that that kind of system exists, because starting this semester we had an influx of a lot of new members, and it was deemed obviously like a large learning curve that made it even more difficult because there wasn't a lot of knowledge like about the project itself on paper. And so additionally with that comes in hand with just like the hardware complexity that we use. Like with these dynamical servos, they were, as Sarah said, extremely complex, and that made it difficult to test to see if stuff works, because you can't use kind of first principles to get kind of basic things working, and given that there wasn't enough documentation. And another issue that we lost a lot of members for, and like we were able to lost a lot of productivity too, is the fact that we didn't have like a central access to like a ROS system, which was a huge limitation just due to a lot of members having Macs, and making it difficult to learn ROS when can't even access ROS. So, and another thing as well is being more clear on like where like the value that we provide as a project, just so we're more clear on kind of what we're trying to learn and what skills like we're trying to develop, just to make sure like new members are totally clear on like what they're getting themselves into, just to make for us to make better assumptions on like what progress we can complete based on the resources we have. So better resource allocation. So that wraps things up. So if there's any questions, feel free to let us know.
The data set you showed looked awesome. Have you guys considered making that public as just an independent entity besides your project?
100%. I think the results we had for being obviously totally new to just vision itself, like I think it's a great place to start to build even like a tutorial on how we built the data set and how we put that into the model and everything, and publish all the data set as well.
Yeah, especially if someone is willing to write up like an article for the website, that'd be an awesome media post that we could put up just in that process.
Yeah, I completely second that. Another question. So where do things stand in terms of which arm you're using? Because I know that you showed pictures of like the 5 degree of freedom arm doing like the gripper stuff. And then there's obviously the 6 degree of freedom arm too. And I know last semester, like you really were pushing for the 6 degree of freedom arm. So what's all happening there, and what's like the future plan of that?
So far with the 5 degree of freedom arm has it works in terms of the like when you want it to move somewhere, it will move there. The communication issues between the type of servos we're using for the 6 degree of freedom arm have been a recurring problem this entire semester. So even though everything else is working, if you can't properly communicate between the jets and the servos, then we can't get it to move. So all of the testing has been occurring over the 5 degree freedom arm.
Yeah. And did you ever like put something finally on like why it's not working, or is that still like an ongoing bug?
We figured out why it's not working, and we eventually did find a supposed solution, and then it worked and then it didn't. So after multiple Saturdays spending 6+ hours in the Bechtel Center staring at the screen. We made the executive decision to maybe try a different servo type or a different motor of some kind.
And to add on to that, like likely kind of what goes wrong is it's a lot like where boards are fried, servos get fried, something gets fried. So that I think is kind of like what happened, because like I think now the board isn't even responding, like the controller for the servos, or at least the data aspect of it. So yeah, that kind of, we wanted to kind of switch to something that was like just using PWM and kind of control methods that were and electrical systems that we were more accustomed to, instead of trying to reinvent the wheel.
Yeah, that's disappointing to hear, because like the Dynamixel stuff was supposed to be like a premium product, so that you didn't have to deal with anything like that.
Yeah, what I researched them a bit. The main reason that we used them to begin with was because we already had a couple of them, and when I figured, oh, these seem like nice servos, and after some preliminary research, I realized that they were actually fairly good quality servos and theoretically should work perfectly for our solution. The problem we mainly ran into was using it specifically the way we were trying to use it, with not a proprietary controller. Brought in a whole lot of errors that we just did not expect. So it's a lot of the documentation issues, and it does not appear to be either super open source friendly, or it takes a more experienced user. So moving to something a little bit more basic, or what we were planning on doing was, we eventually want multiple iterations of a robot arm design so we can test various different things. So what we might do is we might just take an open source design and pretty much just copy that, and so that we can learn from following an instruction manual essentially, and then we can build off of that instead of trying to reinvent it from scratch, which is what we initially tried to do.
Yeah, I mean, that's a good idea. Can definitely relate to trying to build something from scratch and not realizing the complexity of it. One thing that I do want to point out is I know that the Turtlebot uses Dynamixel continuous rotation servos as the motors. And I know that they actually do have an open source controller board called the OpenCR. So I don't know how easy that is to work with, because like whenever I've used a Turtlebot, I just sort of used it as a black box and I didn't mess with any of that stuff. So if in the future you guys do want to give another stab at it, it might be worth looking into that. Or not, I could completely understand why you want to just keep going with PWM, you know, like if it ain't broke, don't fix it.
Yeah, in the future, it would be nice to utilize these servos that we have, but I think in terms of getting the arm, the functional robot arm as fast as possible, it might be best to use a proven approach.
And it does go against kind of like our initial goal was to make this, you know, open source and to like for anyone to build. And when your servos itself are like $50, that's gonna make things a lot more complicated for anyone to be able to build.
Yeah, all good points. Okay, are there any last minute questions for Robot Arm or any of the projects in general before we move on to the next portion of the meeting? Okay.